Right now, a wave of calcium is flooding your synapses. Your brain maintains its wiring in tiny, constant repairs. Think of myelin as insulation on electrical wires. Some paths need thicker coating than others based on what they do. Where you think memory lives, or how calm feels inside, depends on localized upkeep by these repair crews called OPCs. Variations in their speed and timing aren't just noise, they define the structure itself. We are starting to see that deep stillness might actually be optimizing this biological maintenance rhythm across your whole system.
The real complexity emerges when you map function to demand across specific regions of the brain, like a city planning different infrastructure needs. Some pathways are high traffic, demanding constant overhauls, while others maintain a quieter, steady state. Researchers found that how these repair cells, oligodendrocyte progenitor cells, manage their pacing differs dramatically depending on what they are supporting in white matter tracts. It is less about overall maintenance and more about localized upkeep protocols dictated by the system's functional geography.
Something nobody expected is that our deepest states of calm aren't just resting periods, they are tuning instruments across every single connection we possess. Imagine your entire brain as a massive power grid where some circuits demand absolute zero noise for peak performance, while others tolerate more fluctuation during heavy load. That specialized need forces the repair cells to adapt their very timing mechanism. Their internal clocks shift based on regional structural needs. This concept of inherent localized maintenance protocols suggests that achieving deep attunement becomes an active command over your biology's efficiency itself. But if subtle resonance can optimize this delicate upkeep, what happens when we force those circuits into a higher state?
And what happens when that delicate upkeep hits a different frequency? We start looking at how specific demands affect those repair cells in ways nobody expected. Imagine regional load acting like traffic on a pipe. Too much strain, and the whole flow gets disrupted locally. What we are observing is a direct link between sustained low arousal states, that quiet resonance, and actually stabilizing the structure itself. It suggests deep calm isn't just resting, it's actively reinforcing the physical architecture below. But beware of these findings. Some early models suggest that rapid, intense input causes faster turnover, contradicting this whole notion of pure stabilization. If sustained inner harmony can build something up slowly and deeply, how do we manage moments when structure itself seems to fail under pressure?
The system's adaptive capacity is rooted in these repair crews, those oligodendrocyte progenitor cells. We thought stability was just pausing activity, but what we are truly seeing suggests that deep resonance actively directs how specialized structural maintenance happens region by region. Think of it like tuning a precision instrument, where slight adjustments don't fix the string, they change its fundamental vibrational mode for future notes. These localized demand thresholds define whether your connection stays robust or starts fraying under subtle internal pressure. The question now shifts from passive calm to active calibration. How does this biological responsiveness translate into real-world measures of our experience?
And what if that calibration point is dictated not by internal flow, but by external friction? What if a system struggling under persistent, uneven demand reveals something far beyond simple localized wear and tear? We found connections suggesting certain patterns of sustained low-level systemic discord map directly onto unique regional maintenance thresholds in those repair crews. Picture this. Some pathways are like perfectly smooth fiber optic lines, demanding steady current. Others operate more like an aging copper mesh, constantly fighting subtle impedance changes over time. This disparity hints at a deeper, underlying regulatory architecture that we have only just begun to trace across the entire field of neurological function.
The structural integrity that determines your internal states isn't purely passive. It demands active calibration across every system boundary. We discovered a tangible link showing how sustained inner harmony correlates with measurable shifts in this underlying myelination biology, moving beyond just feeling better toward actualizing physical refinement. Imagine tuning an entire complex orchestra, not by silencing the loud instruments, but by subtly adjusting their intrinsic resonant frequency so they support each other perfectly through any passage of music. This suggests that what we perceive as cognitive clarity is actually a quantifiable measure of optimized homeostatic maintenance at the cellular level. We are beginning to map those systemic shifts onto non-invasive biomarkers. The full research archive is at jmthomasofficial.com. The true breakthrough isn't just finding patterns, but designing a map of what that clarity actually means structurally. We are moving beyond simple feeling toward verifiable biological command over how your own system maintains itself. Think of optimizing myelin turnover like fine-tuning an antique clock. Every slight adjustment changes the long-term beat without making it louder or quieter. This capacity for systemic adaptation is tied to those localized maintenance thresholds we observed earlier. The ultimate takeaway is this: recognizing and sustaining that deep internal state isn't a passive benefit, it's actively engineering superior structural resilience across your entire neural architecture. For the full research archive on how these dynamics map onto measurable biomarkers, go to jmthomasofficial.com.